Hello, this is Dr. Joe Trout from the Physics program at Stockton University. Today we'll cover Chapter 15, an introduction to the Sun. If we look at the Sun, which is our local star, it's a pretty average star, okay, but it's still pretty interesting to study. We'll talk about things like solar flares and coronal mass ejections, and like the one we see in this photograph from the Sun. The sun's pretty highly dynamic, which means there's lots going on and there's lots of motion inside the star. And this image combines two satellites' pictures of the sun. The inner one is from the Solar Dynamic Observatory, and the outer one is from the Solar and Heliospheric Observatory. So if we look at the Earth compared to the Sun, the Earth is shown to scale with parts of the Sun with a giant loop of hot gas erupting from its surface. The inset shows the entire Sun in a smaller picture. What we see is that the Sun is many times, hundreds of times larger than the Earth. And even just the loops of hot gas that erupt from the sun are much greater than the size of the Earth. We have Cecilia Payne Gaposchik in her 1925 doctoral thesis laid the foundation for understanding the composition of the sun and the stars. And in her dissertation, she proposed that the sun was made up mainly of hydrogen and helium. If we look at the parts of the sun, we see that we start with a hot core where all the energy is generated and through the regions where the energy is transported upward. So we have this hot core where we have most of the energy being generated. And the energy is first transported by radiation, and then by convection, and then out through the solar atmosphere. The parts of the atmosphere are labeled this photosphere, the chromosphere, the corona. And some typical features in the atmosphere are shown, such as the corona holes and prominence, which we'll discuss in a little bit. But here we see this hot core where all the energy is being generated. And then if you remember, radiation is energy transport through electromagnetic waves. And then we see convection. So what happens is we get this hot gas that rises to the top and cools and comes back down, and we get these convective currents. So we start with the core. We go out to the radiative zone, and then to convection zone. Then we have the photosphere where sunspots will occur, and we'll talk about what these are. And then out to the chromosphere and the corona, which comes off the top of the atmosphere. So if we look at the solar photosphere plus some sunspots, here we see a photograph of the photosphere. And this is the visible surface of the sun. Also shown is a large image of a group of sunspots, and the size of the Earth is shown in comparison. The sunspots appear darker because they are cooler than the surroundings. The typical temperature at the center of a large sunspot is about 3,800 Kelvin, whereas the photosphere surface is about 5,800 Kelvin. If we look a little closer, we see this granularity pattern and the surface markings of these convective cells. They create this granulation pattern on like from this dramatic image taken from a spacecraft. And you can see the same pattern when you heat up soup or oil. What you'll see is that the bottom becomes hot, it expands and rises, it gets to the top and cools off, and then sinks back down to the bottom. So if you're boiling water, you're quite familiar watching this happen. So if you look at the sun's atmosphere, this shows a composite image showing the three components of the solar atmosphere. And they are the photosphere, or the surface of the sun taken in ordinary light, and the chromosphere, and this is imaged with the light of a strong red spectral line of hydrogen. So we're just looking at the red part of the spectrum. And finally, the corona as seen with X-ray. So don't forget, X-rays aren't visible, but we color them here to show their intensities. If we look at the temperature of the solar atmosphere on this graph, and the temperature is shown increasing upward, and the height of the photosphere is shown is increasing to the right. And note the very rapid increase in temperature over a short distance in the transition zone between the chromosphere and the corona. So what we see here is at the beginning, we have a really hot center, and then it cools off a little bit. So we go from about 10 to the 4th Kelvin to about 3 times 10 to the 3rd Kelvin, or about 3000 Kelvin. So here we see that we would get the hot gases rising up and cooling off into this little slightly outer region. Then we see the temperature in this photosphere begins to rise, and in the chromosphere, the temperature is reasonably constant, just below about 10 to the 4th Kelvin. Then in a very short period, so that took from about 0 to about 2,000 kilometers. And then we go from 10 to the 4th up to 10 to the 6th in only 500 kilometers. So in a very short distance, the temperature rises significantly. Here we see a portion of this transition zone, and this image shows these giant ribbons of relatively cool gas that are threading through the lower portion of the hot corona. And the term for these are the filaments, and they're made up of many individual threads. So time-lapse movies of this filament show that it gradually heated as it moved through the corona. And scientists study events like this in order to try to understand what heats the chromosphere and the corona to high temperatures. And the whiskers at the edge of the sun are speculas and jets of hot gas that shoot material up from the sun's surface and disappear after only a few minutes. So this single image gives a hint of how complicated it is to construct a model of all the different structures and heating mechanisms in the solar atmosphere. This is known as a coronagraph, and it shows the image of the sun. It was taken in March 2nd of 2016. And the large dark circle, is the center of the disk that blocks the sun's glare. So we wouldn't be able to see this. We're not normally able to see this because the sun is so bright. But if we block off the really bright spots, we allow us to see the corona. And the small inner circle is where the sun would be if it were visible in this image. we find that there's a coronal hole, and this is a dark area that's visible at the sun's south pole on the Solar Dynamics Observer spacecraft, and we can see a picture of this. So that's this dark region down at the South Pole. So the sun shoots off these hot gases, which are highly charged particles that are moving pretty fast, and they come down to the Earth. And as we said before, these hot charged particles get caught in the Earth's magnetic field. And this colorful glow in the sky is a result of the charged particles in this, what we call the solar wind, as it interacts with the Earth's magnetic field. It used to be thought that the sun was like this perfect sphere of burning gases and that it was the same all the way around. But what we now know is that we have these things called sunspots. And this shows an image of these sunspots. And sunspots are cooler and thus darker regions of the sun. And this one was taken in July of 2012. And you can see the dark central region of each of the sunspots called umbra. And they're surrounded by the less dark regions called penumbra, which are terms you heard when we talked about eclipses. The largest spot shown here is about 11 Earth diameters wide. And although the sunspots appear dark when seen next to the hotter gases of the photosphere, an average sunspot cut out of the solar surface and left standing in the night sky would be just about as bright as the full moon. And the muddled appearance of the sun's surface is the granularity. These sunspots rotate across the sun's surface, and this sequence shows the photographs of the sun's surface and tracks the movement of these sunspots across the visible hemisphere of the sun. And this was taken on March 30th of 2001. And this group of sunspots extended an area of about 13 times the diameter of the Earth. And this region has produced many flares and corona mass injections. These mass ejections are also followed by changes in the magnetic field. So these photographs show how the magnetic fields in sunspots are measured by means of something called the Zeeman effect. And the vertical lines indicate the position of the spectrograph slit through which the light passed to obtain the spectrum shown on the right. So the sun has a strong magnetic field just like the Earth does. And here we see a magnetogram and the solar cycle. And in the images on the left, called the magnetogram, we see the magnetic polarity of the sunspots. The black areas are where the magnetism is pointing towards the sun core, whereas the white regions are where it is pointing away from the core towards us. And this dramatic sequence on the right shows the activity of the cycle of the sun. So these 10 maps of the magnetic field on the surface of the sun span a period of about 7.5 years. The two magnetic polarities, north and south of the magnetic fields, are shown against a blue disk as dark blue to the black north, and as light blue to the white as being south. The earliest image is taken on January 8th, 1992, is at the lower left, and it was taken just after a solar maximum. And each image to the left and to left to right around the arc was taken about 1.5 to 1 years. The time between each photograph is about 1.5 to 1 years, 1 year. And the last image was taken on July 25th, 1999. And this was as the sun was approaching its next solar maximum. So note that there's a few striking patterns in the magnetic maps, and the direction of the white to black polarity in the southern hemisphere is opposite to that of the northern hemisphere. So if we think about a magnet that's rotating, and here we see magnetic field lines that go through the sun. But because the sun's spinning, what happens is these magnetic field lines become disrupted. And the center of the equator of the sun is moving faster than the poles of the sun. So we see is that these magnetic field lines, in essence, get pulled by the rotation of the sun. And they tend to wind up as shown, and after a while, they'll make loops. And once again, this is just an idealized diagram to give you an idea of what's happening with these magnetic field lines. It's really much more complicated than that. We also see these plages on the sun, and this is an image of the sun which was taken with a filter that transmits only the light of the spectral lines produced by a singly ionized calcium. What we see is there's a bright blue cloud region, are the Pleiades. We also have things called prominences, and this shows an eruption of a prominence, and it was taken in the light of a singly ionized helium, and is in the extreme ultraviolet part of the spectrum. So the prominence is a particularly large one, and an image of the Earth is shown to show you that's drawn to scale. So the prominence is a huge cloud of relatively cool gas, about 60,000 K, and it's fairly dense gas suspended in a much hotter corona. And these pictures, of course, were taken with ultraviolet. So don't forget, this color was coded so that white corresponds to the hottest temperature and dark red to the cooler ones. So the 4 images were taken moving clockwise from the upper left on May 15th, May 28th, January 18th, and February 2nd as we rotate through time. We also see solar flares, and this is a bright white area seen on the right-hand side of the sun. And in this image from the Solar Dynamics Observer spacecraft, and it's a solar flare that was observed on January 25th in 2015. So these flares and coronal mass ejections, we see a sequence of 4 images which show the evolution over time of this giant eruption of the sun. And in A, we see the event began with the location of a sunspot, actually a sunspot group. And in B, a flare is seen as in the far ultraviolet. So B was taken with ultraviolet light. And if we look at C, this is 14 hours later, and we see the corona mass ejection is seen as blasting out into outer space. And if we look at D, this is 3 hours later, where this corona mass ejection has expanded to form this giant cloud of particles escaping from the sun. And it begins its journey through the solar system. The white circles in C and D show the diameter of the solar photosphere. And the larger dark area shows where the light from the sun has been blocked out by a specially designed instrument to make it possible to see this relatively faint emission of the corona from the corona. If we look at the solar cycle, what we see is that the period of the number of sunspots has a period of about 11 years. So every 11 years, it reaches a maximum and then goes to a minimum and then repeats. So this is an average. The period can be as short as 9 years and can be as long as 14 years from what we observed. So here we see these dramatic images were taken by the SOHO satellite over a period of 11 years, and it shows how these active regions in the solar cycle. So once again, this was taken in an ultraviolet region of the spectrum, and it shows the active regions of the sun increases and decreases during this cycle. So the sunspots are located in the cooler photosphere beneath the hot gases shown in this image. And they vary in phase with their emission and from these hot gases. So more sunspots, more emission from the hot gases occur together. We view this solar activity with different regions of the spectrum. So for instance, here we see 4 images of the solar flare taken on October 22nd of 2012. And if we start from the left, we have light from the sun at a wavelength of about 171 angstroms. And this shows the structure of the loops of the solar material in the corona. Then we see ultraviolet at a wavelength of about 304 angstroms, which shows light from the region of the sun's atmosphere, which flares originate. Next, we see an image at 335 angstroms, and this highlights the actual radiation from these active regions in the corona and the magnetogram. And finally, we see the magnetogram, which shows the magnetically active regions of the sun. Note that these different types of activity all occur above a sunspot region with a strong magnetic field. So what you can see is at 171 angstroms and 304 angstroms and 335 angstroms. And here we see that this is the sunspot with this strong magnetic signature. So the International Space Station is seen above the Earth, and it was photographed in 2010 by the departing crew of the space shuttle Atlantis. So the NOAA Space Weather Prediction and Operations Center studies the space weather and how the solar winds are going to affect the Earth, right? So this leads workshops on preparedness events for geomagnetic storms, which will come in from the sun. So if we look at the monthly average sunspot numbers, right? So if we, the number of sunspots over time, and this diagram shows the number of sunspots has changed with time since counts of the number of sunspots began being recorded in a consistent time. And note the low number of spots during the early years of the 19th century, where we had the little Maunder minimum. So if we see there's 1, 2, 3, 4, 5 of these peaks going between 1950 and 1800. So we see it about an 11-year cycle, right? So if we check again, right, we have 1, 2, 3, 4.5 peaks, right? So we see that the average period of these of the cycle to be about 11 years. Okay, thank you. And next time we'll talk more about the sun.